Hello, geniuses. Let's take a look at some geometric sequence problems. What makes a sequence geometric is that we need to be constantly multiplying by a same number or a same ratio from term to term. For example, 2, 4, 8, 16, 32. Each step of the way we're multiplying by 2. Okay, they're claiming this is a geometric sequence and we're supposed to find the first 5 terms. Hopefully we recognize this type of a structure or this type of a definition as being recursive. There's a vocabulary word for the day. A recursive definition generally tells us what the first term is and generally gives us a structure involving a sub k plus 1. A common mistake in my mind that people make is that they read this as ak plus 1 equals 1/3 ak. I would rather read this as to get from a given term to the next term, we multiply by 1/3. In my mind, I see recursive definitions as a ladder. In this case, the first rung on the ladder is 81, and we need to step up to the 5th rung of the ladder. This recursive definition tells us to get from the first term to the second term, we multiply by 1/3. So 1/3 of 81, 27. To get from the second to the third, we multiply by 1/3. 27 times 1/3, 9. 9 times 1/3, 3. And 3 times 1/3, 1. A more algebraic approach to this would be to say that A2 is equal to 1/3 times A1, the term that precedes it. In this case, of course, that's 1/3 times A1, 81. And that starts the ball rolling with our second term, 27. Now, for the nth term, we're going to take a little look here at our sequence, which we discovered was 81, 27, 9, 3, 1, and clearly we divide by 3 each step, or maybe more importantly to see, we're multiplying by 1/3 each step. Repeated multiplication, such as 7 times 7 times 7 times 7 times 7, would be nicely grouped with an exponent. So we're going to want to put an exponent on 1/3. So I'm going to set up the nth term formula as an equals our first term, 81, times 1/3 to the, I need an exponent to go with this 1/3. And it's very tempting to put n there, but to get from 81 to 1, to get from my first term to my 5th term, it took 1, 2, 3, 4 multiplications by 1/3. So to get to my 100th term, I would have to multiply by 1/3 99 times. To get to my nth term, I have to multiply by 1/3 n minus 1 times. And there is our nth term. Okay, here's a pretty common problem that we may see where we're asked to find a specified term, in this case the 8th term of a geometric sequence given 2 terms. We certainly would be interested in knowing what our common ratio is. It is 2 steps to get from the first term to the third term. That means starting with 5, we'd need to multiply by our common ratio twice to get to 45/4. So a pretty simple little solve from here. R squared equals, divide both sides by 5, and I get 9/4. Therefore, R is square root of both sides, but of course that means plus or minus square root being 3/2. Now we need to find the 8th term. To get to the 8th term, we can start at the first term and start multiplying by our common ratio. In this case, plus or minus 3/2. But how many times will we multiply by plus or minus 3/2? The number of steps it takes to get from the first term to the 8th term, 7 steps. And some quick calculator work at this point, if we leave this as a fraction, ends up becoming 85 and 55 128ths, and that would probably be the most common mistake at that point, because of course when we take a plus or minus, positive or negative to the 7th, we may get a positive or a negative result. So plus or minus 85 and 55 128ths. Okay, let's take a look at problem number 31. We're finding the nth term of a geometric sequence, and I'm given the second term, and I'm given the 5th term. And the key, as we've talked about before on these types of problems, we need to think in terms of numbers of steps. From the second term to the 5th term, first term, second term, third term, 4th term, 5th term, we've got 1, 2, 3 steps. Since it's geometric, 3 steps of a common multiple. So that brings us to negative 18 times r to the 3rd, our common multiple ratio, equals 2/3. Or, of course, r to the 3rd is 2/3 times negative 1/18, or r to the 3rd is 29 negative 1 on 27. Very nice problem for us, because r would then equal the 3rd root of negative 1 on 27, or negative 1/3. So we multiply negative 1/3, multiply negative 1/3, multiply negative 1/3, we should arrive at 2/3. So to find the nth term of a geometric sequence, we need to know the first term right here. Now I'm moving backwards, so rather than multiplying negative 1/3, I need to take negative 18 times the reciprocal of negative 1/3, or negative 3. So we learn our first term should be positive 54. And now I'm in business. I'm supposed to find my 6th term here. And my 6th term, a couple ways we could get there. We could just start at our 5th term, which would be very convenient. But had they asked for the 53rd term, or something not quite as convenient as the 6th term, here is our nth term. Our formula for finding our nth term is we start at 54, we continuously multiply by negative 1/3. How many times to get to the nth term? N minus 1. So then we could put 6 in for n, and we've got it. But in this case, to get to the 6th term from the 5th term, 2/3, our 5th term, I'm just one multiplication of negative 1/3 away. So 6th term is negative 2 on 9. Problem number 36, we're to find a formula for the nth term of a geometric sequence. Since they're nice enough to tell me it's geometric sequence, I know we have a common ratio. In this case, I see from 4 to 8 and 8 to 16, we're multiplying by 2. So our common ratio is positive 2. And then we're to find an indicated nth term being the 22nd term of this sequence. That shouldn't be too bad for us. The 22nd term equals the first term times times 2 to the number of times or the number of steps it takes us to get to 22. And from the first term, the 22nd term is 21 steps away. So quick calculation in my head, 4 times 2 to the 21st is 8388 608. So there we have it. We learned in that case that geometric sequences, even in very short spans of time, like just to the 22nd term, can get very big in a hurry. Okay, 48 brings us to a summation problem. And because we're only doing a sum from 1 to 6, we could probably handle this one directly by hand rather than using a new formula. But we're going to take a look at that formula as we go through this problem. So I'm going to allow I to start at 1. And I see this is the only place I'm inserting I. So I get 32 times 1/4 to the 1 minus 1, or 0th, plus my second term, 32 times 1/4 raised to the 2 minus 1, or first, plus 32 times another 1/4, this time raised to the 3 minus 1, and plus dot 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 until I get to 32 times 1/4 to the 6 minus 1, or fifth, giving us our 6 terms. And I see that my first term, 32 times 1/4 to the 0, would be 32 times just 1, or 32, plus 32 times 1/4, 8, plus 32 times 1/4, 8, times another 1/4, 2, plus dot, 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 until I get to 32 times 1/4 to the 5th. Okay, we could certainly write those terms out. We're going to get some fractions, add some fractions along the way. But I'm going to go ahead and take you to the formula for this. And we are looking for the sum of 6 terms. The first 6 terms from 1 through 6. The sum of the 6 terms of a geometric sequence would be equal to the first term, 32, times big parentheses, 1 minus our ratio. Well, our ratio is pretty clear. Each step we multiply by another 1/4. So our ratio is 1/4, and we raise that ratio to the 6th power. And that is all on just 1 minus the ratio, 1/4. And then at this point, we could probably impress some 7th and 8th graders, but we're going to go ahead and just run this guy through our calculator, and we get S6 should end up being 42.65625. And that's our setup. If you need further information on this formula, it is attached on our website down in the notes section. It's also in your book. Okay, we are looking at problem number 58, where we're to use summation notation to represent this sum. And This is a geometric sequence that's given in the book, and for a geometric sequence, we're always interested in finding our common ratio. If we know we have a geometric sequence, one easy way to find the ratio is to take the second term and divide it by the first, and we get -3 on 15, or our ratio is -1/5. The next challenge presented here is we have to figure out how many hidden terms are represented in the dot dot dots. So I'm going to continue multiplying by -1/5 to get from 3/5 to -3 on 625. The 3 is not very revealing because of course it's going to stay a plus or minus 3. But we need to get from 5 to 625. Just some quick computation because we're not far from it. 5 times 5, of course, 25, times another 5 gets us to 125, and times another 5 gets us to our 625. So I have two terms between here. I have an on 25 and I have an on 125 before we get to 625. So we're dealing with 1, 2, 3, 4, 5, 6 terms. N is 6. So I'm going to go ahead and make the formula for the nth term of our sequence. The nth term of our sequence, as we've seen before, we start at our first term and we start multiplying by our ratio, -1/5. How many times do we multiply by that ratio? How many steps are there from the first term to the nth term? n-1. That gives us the basis for our summation notation, where we're going to go for n equals 1 up to 6, 15 times -1/5 raised to the n-1. And we've got it. All right, here's the famous frog on a log problem. I like to use this to illustrate an important concept about geometric sequences, and that is that the sum of an infinite geometric sequence may not, in fact, be infinity. So here is the precept of this problem. Let's say we have trained our friend here, the frog. Say we've trained our frog to be able to jump half the distance to the end of a log on any given jump. And let's say for starters that our log is 8 foot long, and we place the frog over here at the end of the log. And we start letting that frog jump, and let's say that frog makes a jump every couple of seconds, and we start recording his jumps. So the frog's first jump halfway to the end of the log is a leap of 4 and places him over here. And then he takes his second jump a couple of seconds later, and half of the distance now left is just 2. And he takes a third jump, and half of that distance is 1, and a fourth, and a fifth, and a sixth. And we get tired of recording, so we say we're going to come back tomorrow and check on this frog's process. And by time we get here tomorrow, the frog is down here, and we can barely see that frog jumping. And we say, wow, he's not making very much progress. And we come back a year later, and there's our tired and hungry frog, and we can't see him making any forward progress at all. And he has virtually gone the length of the log, 8 feet. And in theory, if that frog could make infinity jumps, he would actually end up jumping 8 feet. That ties into our formula for an infinite sum, which says The sum of an infinite sequence, sum of infinity terms, is the first term, or in this case the first jump, over 1 minus the ratio. In this case, each jump is half as far as the previous jump. Our frog's jump, first jump, is 4 over 1 minus 1 half, and that equals 8. Okay, let's find the sum of an infinite geometric sequence. We have a formula for that, which says the sum of an infinite geometric sequence is a1 on 1 minus r, but it also says that the absolute value of r must be less than 1. In other words, we have to be multiplying by a fraction or a decimal between -1 and 1 for this to work. The nice thing about this form, summation form, is usually a1 and r are staring us right in the face, and that's the case on this problem. But let's take a look at a couple terms. Our first term when n equals 0 would be 9 times -2/3 to the 0th, or 9 times 1, 9. Plus our second term when n is 1, 9 times -2/3 now to the first. And at that point, we quickly see each step we just multiply by another -2/3. That's our ratio. In this case, we end up with -6. Our following term, 9, and here we go again, times an extra -2/3 to the second. That would give us +4. Our following term, if you check it when n is 3, would give us -8/3, and we would just go on and on from there. It's nice that we have a formula for this. So in frog speak, our frog makes an initial jump of 9, but then jumps backwards 6, and then forward 4, and backwards 8/3, and on and on and on and on, and the jumps get shorter and shorter. So our formula, sum of our infinity frog jumps, is our first jump, 9 over 1 minus our ratio, -2/3, and yes, again, the negative matters. We get 9 on 1 plus 2/3, 5/3, or 27/5.